So far we have calculated the energy of SiMO plus and we have noticed that this energy is less than the U1s. Now we are going to make a plot of electron distribution of SiMO plus. In order to do so, we have to first know the what will be the wave function for individual atomic orbital, that is phi 1sa and phi 1sb. Both the atomic orbital will follow a exponential decrease from the central point, that is the nuclear point. That is the characteristics for your individual atomic orbital. Now these atomic orbitals will add to form a molecular orbital which is SiMO plus. If I add these two functions, then I will have a plot which is presented in the red line. That is my wave function of wave function corresponding to SiMO plus, that is molecular orbital which formed by the additive combination of two atomic orbital phi 1sa and phi 1sb. What we have noticed here that there is an increase in the value of wave function in the every point in between the internuclear axis. Now if you recall that the electron density of a system is represented by the square of its electronic wave function. Here all phi 1sa, phi 1sb, SiMO plus all are electronic wave function. So what will happen if I square this term? Everything look like the similar, but the magnitude will increase. So again we will notice that the electron density in between for the SiMO plus is higher in between the position of nuclei A and nucleus A and B, that is the along the internuclear distance. We found there is an increase in the electron density, okay, in both the sides. This is positive phase, this is negative phase. So we can noticed like a cylindrical distribution, that is a increase in the electron density along my internuclear distance, which is nothing, is the bond between two hydrogen atom A and B. Now this cylindrical distribution tells me that that is looks like a bonding electronic orbital. So SiMO plus is known as bonding molecular orbital. Okay. Similarly, we have another combination to get the SiMO, and that will be SiMO minus, which is obtained by the subtraction of SiMO phi 1sa minus phi 1sb. That is, if you recall this, if you recall the combination, this one, this plus combination is SiMO plus. If I forget this plus combination, that means my minus combination, this minus combination will be my SiMO minus. And if I take the plus combination, then it will be SiMO plus. We have carried out all the things for plus combination. Now we want to find out the energy for minus combination. Okay, for minus combination we want to, and we are designated this combination as SiMO minus. That is, this is the SiMO minus. This is my SiMO minus. Okay. Now if I calculate this SiMO minus, then I will have encountered similar type of Hamiltonian operator, similar kind of operation. There will be 16 integral term. Then we can go only what will happen, and in this case I have my in constant will be 1 minus SAB, and these two terms appear as similar to the SiMO plus, and next a term which is we have noticed J plus K 1 plus SAB. For the SiMO plus, here we will obtain J minus K by 1 minus SAB. That is the difference only here. Now if we calculate, this term will be positive. Again this term also becomes positive for this case. Okay. Now these two quantity will make the things positive. So what will we obtain? We will obtain that the psi mo average energy of psi mo minus will be greater than U1s. And if we draw the wave function plot, that is one wave function in the positive direction, another is in the negative direction. So the combination of these two will make a line. This is the red line which will pass through a point where at the internuclear axis, where at the electron density, where the wave function value of wave function will be 0. Similarly, if you make the square, all the things become similar, only the magnitude will increase. So the electron density for the psi mo minus will pass through a minimum which is 0, through a 0 point. So at this point, which is actually the middle of this RAB, that is the internuclear distance between A and B nuclei, will be make 0. So what will happen? And again you can notice along the internuclear distance, always there is a decrease in the electron density from the actual density of your actual electron density of your atomic orbital. That is, the value of this line is always lower than this atomic orbital value here also. So what will happen? It will that means that you have a lower amount of electron density as compared to the atomic orbitals along the internuclear distance. So this psi mo minus is called as antibonding molecular orbital, and these two can be I can present by a molecular orbital diagram. So in y-axis you have energy. Now 1s a, 1s a, 1s b. Now it will form a bonding molecular orbital which is less than the E1s, and antibonding orbital which is has greater than energy than E1s. Now if I going to plot another thing, sorry, if I want to plot another thing, that is the average energy, which is energy also for psi mo plus and psi mo minus, then psi mo plus will be a plot like this. It's a Morse potential energy type curve, and this position will be your R0, which is equilibrium bond distance. Okay, now this will be the equilibrium bond distance, but if you take the psi mo minus antibonding orbital, that will be look like this as the red line. Okay, so it will never ended up with a minima. Now this all we have noticed with a combination which we consider. But if you look at the experimental curve, then what will happen? The experimental lines always have some lower energy than the combination which we have considered for psi mo plus. So what will happen? This can be achieved with the proper method of approximation. That if we consider a variation method, and we can take a trial wave function, and then we can change the trial wave function, and once we reached the energy which is exactly the experimental energy, then this wave function will be the exact wave function of the molecular orbital. Okay, that is the another story of this system. So you can got the exact wave function using a variation method when you have a error 0% error. But we know that the according to variation principle, we have always have higher energy for a trial wave function, and it may be equal to the actual ground state energy when the trial wave function becomes the exact wave function.